welcome back to Philosophy of Science Contemporary Debates. This is our first seminar of semester 2, and it's my very great pleasure to introduce Dr. Eran Tal from the History and Philosophy of Science Department at the University of Cambridge. Eran, as I was just saying to the MSc students in the tutorial, is a rising star in this blossoming field of the history and philosophy of metrology, or measurement. A lot of work has been done in a really recent year, probably a decade, on this area, and it's a thriving field in contemporary philosophy of science. Signs of this rising star is that Eran has already published for the Stanford Encyclopedia of Philosophy, commissioned paper for Philosophy Compass, papers in top journal like BJPS and Philosophy of Science, among others, and is currently the recipient of a Marie Curie Fellowship, which is hosted at the HPS unit at the University of Cambridge. So, very good pleasure to have you here to talk about time, making time, and a study in the epistemology of measurement.
Thanks very much, Tella. Thanks for inviting me here and for this extremely flattering and somewhat embarrassing introduction. Thanks everyone for being here. My talk is titled Making Time, a Study in the Epistemology of Measurement. And you may be wondering, what exactly is the epistemology of measurement? Well, measurement has two main aspects. When you measure, you use instruments. You have a material apparatus or material arrangement that you're dealing with. Clocks, thermometers, rulers, scales. You do things with objects. Even if you're talking about psychological measurements, you still interact with a questionnaire, for example. But of course, there's also an epistemic aspect to measurement, because what we want to get when we measure is some knowledge claim. Knowledge claim about an abstract quantity, such as time, or temperature, or length, or weight. And very broadly, the epistemology of measurement deals with the relationship, with the inferences that tie those two aspects of measurement together. So the epistemology of measurement answers questions such as how do material operations feature in the justification of these knowledge claims? What sort of inferences are involved in getting from the results of material interactions to knowledge claims? And what background assumptions are involved in these inferences? How do we justify those background assumptions? And in this talk today, I want to speak about a very particular kind of knowledge claim that is absolutely necessary to make any kind of measurement on a ratio or even interval scale, and that's a congruence claim. A congruence claim is a claim of the form quantity interval delta Q is equal to quantity interval delta Q prime. So we have two quantity intervals, such as two temperature intervals, or two length intervals, or two durations. And we're claiming that they're equal. Without congruous claims, we will not be able to measure any quantity on the scales that we are used to in physics, intervals and ratio scales. But how are scientists able to test these claims? And moreover, how are scientists able to test claims to congruence in a reproducible fashion, in a fashion that allows us in Edinburgh and someone in Japan to arrive at the same result? How is that even possible? It's a very fundamental question about measurement. And to give you sort of a taste of the problem behind answering this question, here's an example that I just actually mentioned to the students I met from Ha-Seok Chang's book, Inventing Temperature. Imagine that you're in the early 19th century and you want to standardize temperature. You don't yet have a good theory of temperature, but you know that fluids expand when they're heated. So you fill 3 glass tubes with 3 different liquids. One is mercury, one is alcohol, and one is water. And you fix the 0 and 100 marks on those tubes to the freezing and boiling of water. And you see what happens in between when you measure temperatures somewhere in between the freezing and boiling of water. And something strange happens. When mercury is at the 50 mark, right in between, right in the middle, alcohol is lagging behind at 44, and water is really at 26. It's not even, it's just a quarter of the way. So, in other words, temperature intervals that are deemed equal by one instrument are deemed unequal by another. And it seems like we need to make some sort of choice as to which thermometer to go with, which thermometer is more accurate. To do that, we need to be able to establish the relationship between the volume indications of these instruments and temperature. But to do that, we need an accurate thermometer, which lands us in a loop. There is a kind of circle that we need to escape if we are ever going to establish one of these as an accurate thermometer. And there's been a standard kind of strand of scholarship in philosophy that I'm sure many of you are familiar with, conventionalism. Conventionalists like Mach, Poincaré, Reichenbach, and Carnot had a particular kind of solution to this problem. In very cursory way, their solution is this. Choose a congruence criterion. It doesn't matter which. Choose one of these thermometers and stick with that choice. The choice is arbitrary. So a congruence criterion is a matter of convention. It's once you've chosen a congruence criterion that you can then reproduce tests for congruence. But the fundamental choice is arbitrary. It's affected by considerations of convenience and simplicity, but there's nothing, no empirical tests that need to be performed. And these congruence criteria, once you choose them, they're static. They don't change. They have no history. I want to suggest that the picture is actually quite a bit more complex. My account, which I call the model-based account of measurement, draws lessons from metrology. Metrology is the science of measurement. Metrologists are the physicists and engineers who work at standardization bureaus and maintain units and scales. They maintain the kilogram, they maintain the second, and the meter. And they disseminate it to metrological institutions throughout the globe so that we all get the same results when we measure. And I've spent some time sitting in metrology labs and talking with metrologists, and the account that I'm about to propose draws heavily on my insights from their practice. What I want to convince you today is that the way congruence criteria apply to concrete measurements is not completely fixed by definition. And that what counts as a proper application of a quantity concept or a congruence criterion depends on how you model measuring instruments. That is, it depends on an idealized representation of the measuring instrument and the assumptions, the theoretical and statistical assumptions that go into that representation. And this process of standardization is not static. These models that metrologists construct of their instrument need to be continually tweaked, continually changed in order to maintain reproducibility. So let's see what the general outline of the next few minutes will be. I'm going to give you my main case study, which is going to be the standardization of time, coordinated universal time. And I'm going to briefly discuss the conventionalist solution to problems of congruence and reproducibility, and followed by my own account, and finish with a few concluding remarks. Okay, so universal coordinated time. Coordinated universal time is the time that your cell phones and your computers are calibrated to. it's the key standard timekeeping standard for civil and scientific uses, and it's replaced. I know a lot of us still think of Greenwich Mean Time as that standard. Actually, according to the Universal Time, replaced Greenwich Mean Time in 1972. UTC is maintained and disseminated by the International Bureau of Weights and Measures near Paris, and we're going to go into the nitty-gritty of how exactly you get all our clocks to tell roughly the same time. But how is it even possible? How do they succeed in making all our clocks tell the same time? If you want to synchronize clocks all over the globe, there are two things you're mainly interested in. The first thing you're interested in is frequency stability. That's, you want your clocks to tick at a uniform rate. You want your clocks to mark equal intervals of time. And the second thing you're interested in is frequency accuracy. You want your clocks to tick at a specified rate, say 1 tick every second. So there are two things you need to fix. One is the standard of uniformity, which is you need some standard for the equality of time intervals, which is exactly the problem we have. We want to be able to fix that. We want to understand how metrologists are able to test claims to the equality of time intervals. The second thing you need is a time scale, some scale and unit on which to measure time. Ideally, and the word ideally is very important here. Ideally, all you need to do is these two things. First, you need to define the second. And the second is currently defined by the duration of exactly this many periods of the radiation corresponding to a transition between two states of a cesium atom. The idea is that cesium atoms, like all atoms, have energy levels, and there are particular frequencies that are associated with transitions between those levels. And a particular transition has been chosen to be stable by definition, which sounds very much like the conventionalist kind of solution. Right? So by definition, this transition in cesium-133 is this many hertz. Notice that we haven't just defined a unit. We've defined more than just a unit. We've defined a congruence criteria for time in this definition. Next thing you need to do is define a time scale. And that's called the terrestrial time scale. That's the coordinate time scale whose unit is 1 second on sea level. And sea level is important because of general relativity. Clocks tick at different rates under different background gravitational fields. So we want to specify exactly what the gravitational potential is where the clock is. So you do those two things and you're done. Right? Wrong. Because those are just words on paper. You can't calibrate any clock to the words. Right? These are just linguistic or abstract ideas. If you want to make clocks actually tick in uniformity, you have a much rougher time. Because in these definitions I've just given you, cesium atoms are assumed to be at complete rest, at 0 degrees Kelvin. They're not affected by any magnetic fields or collisions with other atoms. So all those things that in reality actually change the frequency of that transition are assumed to just not exist. Sea level is another idealized notion. So sea level is in fact an idealized surface called the geoid that marks equal gravitational potential around the Earth. But no one knows exactly where the geoid is. Okay? It's an idealized construct. So if you want to synchronize clocks the world over, what you need is to approximate this ideal cesium atom sitting on the geoid. You want to build clocks that realize, in metrological jargon, that is, approximately satisfy these definitions. But the problem is that these clocks don't tick exactly the same rate. Each one ticks at a slightly different rate. So you need some sort of trade-off between various desiderata. What metrologists end up doing is they have a trade-off between frequency stability and frequency accuracy. Here's one of the most accurate clocks in the world. It's one of 12 primary frequency standards. This one happens to be in Boulder, Colorado. It's the American frequency primary standard. This machine, except for being really expensive, takes a lot of time and effort to evaluate. Because we want it to be so accurate, what scientists do is they rigorously evaluate every single aspect of this machine. In this machine are cesium atoms that are very carefully controlled, and every little effect, be it temperature fluctuations, magnetic fluctuations, collisions with other atoms, gravitational field, and a myriad of other effects, are all carefully recorded and accounted for. But to do all this, this machine needs to be constantly changed, reassembled, improved, which means it can't actually run as a continuous clock. It actually is mostly off. It only goes on about 5 times a year for about 3 weeks to a month every time to calibrate the more sturdy but less accurate clocks, the secondary standards. Secondary realizations of the second, these are the workhorses. These are the clocks that actually keep the time. They're on for years, but although their frequency is stable, in the long run, they drift off, and they need recalibrations. So you're already faced, imagine yourself being the metrologist, you're already faced with all these different clocks, some of which are more stable, some are more accurate. They all drift relative to each other, and you need to construct one measure of time that would serve all of humanity. How do you do that? And more importantly for us philosophers, based on what kinds of assumptions do you do that, and what inferences do you use, and how you justify those inferences? What metrologists do is they calculate an abstract measure of time, and they call it coordinated universal time, based on the indications of these multiple clocks, and they tune these clocks to that abstract measure. Before I tell you how exactly they calculate it, I'm going to show you the end result. Every month, the International Bureau of Weights and Measures sends out this table. Well, this is just an excerpt. It's a very long table. And in that table, it lists the number of nanoseconds that each nation's national clock is relative to UTC. It's a table of corrections. So you can see that Sydney was 842 nanoseconds behind UTC on October 30th, 2011. What I want you to get from this slide is that you are looking at UTC. Coordinated universal time just is this table. There is no clock that ticks UTC. UTC is a list of corrections that are sent out. It's an abstract model parameter that is disseminated through this list of corrections. There is no concrete process related to it. There are many approximations of UTC, but there is no clock. So how do they arrive at these corrections? Well, there are 3 stages. At first, the International Bureau records the indications of about 400 secondary standards, so those really stable but less accurate clocks that run for a long time. They take indications for about 60 metrological laboratories around the world, and every 30 days they calculate a weighted average of these indications. They weight the clocks based on their frequency stability, which is very nice, right? But it would be nice if you actually knew what the frequency stability is. to assess the frequency stability of a clock, you need to compare it to another clock, preferably one more stable. But those are already the best standards you have. So what the International Bureau of Weights and Measures does is they give higher weight to clocks that retrodicted the weighted average best in the last 12 months. They're effectively using the average as its own standard. They're calibrating the clocks or correcting the clocks based on their ability to predict their own weighted average. And this running, seemingly circular set of calculations is what distributes weights among these clocks. But this, of course, brings new problems in, because now it seems like the clocks that predict each other better are just going to have this positive feedback effect where they just gain weight in their calculation indefinitely. And then, a few clocks will just dominate world time because they happen to be well correlated with each other. And we don't want that. So metrologists also enforce a maximum weight of about 0.9%. But that's not the only problem, because there are occasionally new clocks join the ensemble. So you need to protect the average from frequency and time bumps. You don't want the whole average to have a frequency step, for example. So new clocks get a weight of 0 for exactly 4 months after they're introduced. And moreover, there are these cushion parameters that compensate for jumps. Whenever there's a new clock, there's a parameter that is meant in the calculation that compensates. And you can start to get the taste that there's a lot of ad hoc kinds of maneuvers here. But that's not all, because even after the metrologists have done all this, the second stage is required, because remember the primary standards that we left off somewhere in the basements of the National Institute of Standards and Technology. All those secondary standards, after running for a while in the 50s, started to drift away from the primary standards to the point where there was a real divergence. And since the 70s, metrologists have started adding what they call steering corrections, frequency corrections that are meant to prevent secondary and primary standards from veering off in frequency. That's the next stage. And the next stage results in a measure of time called international atomic time. These corrections are themselves interesting because they introduce yet new challenges to the production of global time. For example, remember primary standards only go on for a little while and then they go off again for improvements and repairs. Well, every time you do that, you pull the whole ensemble of clocks towards a slightly different frequency. You don't want every new calibration to pull the frequency away from where it was. So a new parameter called a memory parameter smoothes those differences. And even that's not enough, because steering too quickly again reduces stability. So there are changing policies about how to deal with these with steering corrections that are either too quick or too slow. I'm not going to go into more details about this process. The detail is in the paper that just came out in BJPS. But as you can see, there are quite a few patches in this algorithm. It feels more like a patchwork than a sort of thought through inference from evidence that we would like science to produce. And we need to, I think as philosophers, we need to take this seriously and try to make sense of what metrologists are doing. Before making sense, I want to mention the third stage. It's not important for my talk, but you should know that the last stage is in the calculation of UTC is just meant to make UTC in line with our experience as humans on this planet, where the duration of the day is 24 hours. As you may know, the rotation of the Earth is slowing down due to tidal forces, forces that operate between the Earth and the Moon. And for this reason, to save solar time, occasionally a leap second is added to international atomic time. We're currently 35 seconds in, and in July there will be another one. This is an interesting topic in itself, but for this talk I'm just going to focus on international atomic time. So whenever I talk about UTC, what I really mean is UTC before the introduction of leap seconds. Okay. Having gone through all this technicality, let's go back to a little bit of philosophy. We acknowledge that metrologists are really good at what they're doing. I mean, in the end, it's exceptional how well time is reproduced. They must be doing something right. But at the same time, the reproducibility of uniformity is achieved by all these ad hoc corrections, cushion parameters, steering corrections, self-fulfilling assumptions, arbitrary rules. How do we make sense of these from an epistemic point of view? Or are they just bad science? One tradition that deals with these questions that I already mentioned is conventionalism. And the conventionalist account of standardization is this. Conventionalists view claims of the form time interval delta t is equal to time interval delta t prime. Those claims are neither true nor false in themselves. Nature doesn't decide. It's us who decide by convention. Reichenbach called these choices coordinated definitions, which means that they coordinate an abstract concept of in this case, the uniformity of time, with some concrete procedure. So we, for example, coordinate the concept of uniformity of time with the procedure of probing a cesium-133 clock and observing the frequency that we get. Carnap additionally mentions that once a coordinate definition is in place, we're done. So for a conventionalist, once we decide what our congruence criterion is, it's just a matter of running empirical tests to see which clocks are more or less uniform. There's no additional work to be done. So I imagine if I had Carnap or Reichenbach in this room and I would ask them, well, how do you make sense of all of what I just presented? And they would probably claim that standardizing time amounts to testing which clocks conform better to your definition of uniformity, which is the definition of the second. But now the question is, can we understand all of the algorithms, all these maneuvers and ad hoc rules that I've just presented as testing for the accuracy of clocks? Can these algorithmic maneuvers be understood as indicators of how well any given clock conforms to the ideal definition of the second? And I don't think they can be construed as indicators, because indicators are supposed to be sensitive to the thing indicated. That's a very minimal requirement for testing, is that your indicator is sensitive to the thing indicated. And, well, is the UTC algorithm sensitive to the closeness of the clock's period to the ideal second? To some extent, it is. If you think about the long run, these steering corrections that I mentioned do make sure that the frequency of UTC doesn't veer off too much from that of primary standards. And we know that primary standards are very thoroughly modeled, and their uncertainties are thoroughly evaluated. So perhaps in the long run, we can think of those steering corrections as providing some sort of test. But what about all the other inferences and rules that I just mentioned? Especially those that work over the short run. Over the short run, the stability of UTC depends on those secondary standards. And there, I don't think the conventionalist fares very well. In fact, the UTC algorithm is designed to be as insensitive as possible to the discrepancies among the frequencies of secondary standards. So think about what they're actually doing every time a discrepancy occurs among clocks. If the conventionalists were right, metrologists would have to look at all the frequencies they're getting and try to somehow fit a curve through them that would be that would allow them to make some sort of statistical test of compatibility between the ideal second and the indications of their clocks. But they don't do any of that. In fact, they do the opposite. Every time there's a discrepancy, it's the data that is corrected. So on the level of individual clocks, every time a clock veers off, its weight is lowered. Or in serious cases, the clock is simply ignored and scrapped from the list of standards, or replaced with another clock. But also on the level of the average. Every time there's a bump in frequency, it's just ad hoc, smoothed, or cushioned. There is no way in which metrologists, I think, can be construed as testing their clocks for accuracy or stability in this case. So I think whatever these short-term stabilizing mechanisms are doing, I don't think it's detection or testing. And so before I go into my account, there are, I think, three ways to go forward from where the conventionalist left off. One is to say, look, scientists are just doing something wrong. Metrologists are doing bad science. I don't think that's a good way to go, especially not with a case study like this, where it's clear that time is one of the quantities that is standardized in the most reliable way that we know. Another option, which I'm not discussing now, but I'm happy to talk about in the question period, and I talk about it a lot in the paper, is to treat all these algorithmic maneuvers as sort of social engineering practices. So as kind of consensus building practices that allow different metrological institutions to agree on what the time is, but have no epistemic grounding. I think that is also a very problematic way to go, and I can talk about it later. But what I want to do is defend these practices from an epistemic point of view and show that they have, in fact, a real function in establishing the reliability of time standardization. And this is where my model-based account enters. If I'm right, then standardization projects are aimed at stabilizing the way quantity concepts are applied to particulars. And when I talk about stability, there are two aspects. One is repeatability, so stability over time, getting the same result again and again with the same procedure. The other aspect of stability is reproducibility, getting the same result across different procedures, different instruments, and different background circumstances. The key claim is that the mode of application of a quantity concept, how we apply a quantity concept, is determined by the specification of idealized models of measuring instruments. Let's try to flesh out this claim a little bit. Before we can appreciate this claim, we need to be very clear on a distinction that I think the conventionalist muddies. Instrument indications versus measurement outcomes. Those are very different kinds of things. Instrument indications or readings are properties of the instrument in the final state after it's it's performed the measurement. So examples are volume of mercury column in the thermometer, or the position of a pointer relative to a dial of diameter, or a number of cycles generated by a clock. Those are properties of the clock or thermometer or ammeter. On the other hand, measurement outcomes are knowledge claims about the quantity we're trying to measure. So corresponding examples would be a temperature estimate with some uncertainty, or electric current, or duration estimate with some uncertainty. Those are estimates of the value of a quantity being measured. And in some way, you can say that the entire epistemology of measurement lies in between these two. Our ability to infer measurement outcomes from instrument indication is what needs explaining. These inferences from indications to outcomes are not by any stretch direct. They rely on a lot of background theoretical and statistical assumptions about the measuring instrument, its interactions with the object and the environment. We often forget that because metrologists have done their work so well that the instruments we usually use at our home already conceal this difference. We don't notice the inference because we don't do it ourselves. The person calibrating and designing and calibrating the instrument did it for us. We just read a digit off the dial or the display. But measurement outcomes, in fact, can only be inferred once the instrument is subsumed under some idealized representation. And that kind of representation or model is necessary to relate indications to outcomes. And also to determine the attribution of errors and uncertainties to your measurement. And here I come to the first important point for my account of standardization, which is that stability, or the idea of getting the same result, is itself a model-sensitive concept. When we ask, do two clocks agree? We're not asking about their indications. What we're asking is about their outcomes. We're asking about whether our estimates of duration based on these clocks agree. Not about whether the numbers that appear on the display agree. And when we ask about agreement between outcomes, outcomes are model sensitive. They change when the theoretical and statistical background assumptions change. So any claim to stability, any claim to be getting the same result, either over time or across methods, is already can only be understood in the context of these models. Now, how do we understand the calculation of UTC then? What's happening when we calculate this abstract measure of time? Well, what we're trying to do when metrologists are trying to do when they calculate UTC is to subsume hundreds of clocks under a common idealized model, namely the model of terrestrial time. The model of that lone ideal cesium atom sitting on the perfect sea level. We're trying to subsume concrete, messy, noisy clocks in our lab under the model of this ideal, and try to see how far they are different, how far they approximate or fail to approximate that ideal. UTC is a step we take, or that metrologists take on the way. But like I mentioned, you can't calibrate your clocks against an ideal, and the ideal doesn't tick. The ideal cesium atom doesn't exist. So what is required is much more detail needs to be added to that initial highly ideal model. Detail that has to do with the specific idiosyncrasies and properties of the messy clock in the lab. What we in effect get is a hierarchy of models that run from the highly idealized model of terrestrial time all the way to your concrete clock in the lab. You can visualize it in the following way. Here are your clocks, very schematically. And here is a parameter in the highly idealized model, terrestrial time. terrestrial time is the parameter in the model that we. Oh, what happened?
This is not so you can watch it.
Oh, I see. It refers to the time an ideal clock would tick if it had none of the noisy features that real clocks have. And now we want to subsume these clocks under the general idealized concept. We can't do it directly, but what we can do is build a hierarchy of models and model parameters that allow us to mediate these two levels, so that the time indications of any particular atomic clock is considered an approximation of an intermediary model, say at the national level. The UK lab, the NPL, would have its own a model of its own ensemble. Each of these local laboratories would have these intermediary local approximations of UTC, and one step up would be coordinated universal time would be another mediating step on the way to approximating this ideal. In this picture, coordination is not a single step. It's in fact a multi-step chain of approximations. So notice that coordinated. So notice that the direction of the arrows is going up rather than down. These arrows denote approximation relations. We're used to thinking about models as approximating the world, but in metrology we're actually doing something quite different. We take concrete instruments and we use them to approximate ideal parameters. And the reason metrologists are able to do this in the model-based account is because these models play not just a descriptive role, but also a normative role. That is, metrological models have a legislative function. They don't just describe what clocks are doing. Metrological models also, to some extent, legislate how we want to apply the concept that we're standardizing to concrete particulars. So think of it as an abstract representation that in one step allows you to predict what the clock will do, but in the next step allows you to decide whether you want the standardized concept to fit what the clock is doing. It's a kind of iterative process that flips from the normative to descriptive. And if I'm right, then this explains what all this patchwork of ad hoc rules and circles is actually for. Because what happens whenever the data isn't, when clocks aren't agreeing, is that metrologists choose those model assumptions that make the clocks, most clocks, as accurate as possible. So we don't ask which model approximates clock behavior in the best way. We're actually asking which model allows us to apply the concept of time uniformity in a way that makes our clocks in the lab come out as most accurate. Okay? It's a reversal of the usual way we think about models. That's a legislative function of models. And that's exactly the kind of special function that metrological models play. They don't just describe our instruments, they also legislate the mode of application of the quantity concept to those instruments. And this, I think, explains the function of short-term stabilizing mechanisms that we talked about in UTC. Remember that stability is a model-sensitive notion, so that metrologists actually have the leeway of deciding which assumptions to use in order to achieve stability. Stability isn't just read off the display of an instrument. Stability can be tweaked or increased by changing the way you present your instruments. And that's the key move in explaining what seems like bad science, but is in fact, I think, completely justified from an epistemic point of view. I'm not saying that metrologists can do whatever they want. I'm not saying that metrologists can just construct any model and make any clock accurate just by sheer convention. This is it's not at all arbitrary how you model these clocks. In fact, these iterative kind of modifications are tightly constrained by empirical facts, because UTC is not the only standard of time. There are several standards of time, and there are also standards for other quantities that are, of course, related to time, so that metrologists only have leeway within the constraints of coherence among different measuring instruments and different scientific results. They can't just ad hoc bring their clocks into complete agreement, but what they can do is tweak their models in a way that makes them the most congruent as possible, the most convergent as possible. And the bottom line is really quite a departure from conventionalism as we know it. Congruence criteria end up being neither completely arbitrary, nor a priori, and not static either. They're historical, they change. In fact, they change every month. So just to conclude, what I've argued is that measurement outcomes are model sensitive. They depend on theoretical and statistical assumptions under which instruments are modeled. And I've also argued that metrologists are to some extent free to modify the proper mode of application of the concepts they standardize. They're not completely free. Once they define, they cannot completely arbitrarily choose which instruments are more accurate than others, but they have some freedom within the limitations of constraint, within the limitations of coherence, to tweak the models they use. And they use this freedom to increase the stability of their ensembles of instruments. And as I said, the reproducibility of congruence tests depends on an iterative process of dynamic stabilization. It's not a static kind of definition, and involves modifications to instruments and the models that represent those instruments continually. There are several interesting consequences from this that I'm glad to explore in the question period. One, I just mentioned one interesting and slightly counterintuitive consequence of this is that it's precisely because idealized theoretical definitions don't completely determine the mode of application of quantity concepts that stabilization is possible. So we usually think of undetermination as a problem, right? We read Duhem, we read Quine, and we think, oh, it's a problem because, wouldn't it be nice if evidence completely determined our theories and models? Well, in fact, undetermination is not a problem for metrologists. It's the opposite. It's a precondition for their work, for the possibility of their work, because it's only because the mode of application of quantity concepts is undetermined by the definitions of those concepts that metrologists are able to tweak and bring instruments into agreement. Without this flexibility, standardization, as we know it, would be impossible. And that's one of several counterintuitive consequences of this account that I'm happy to explore in the question period. Thank you very much.